Hello, everybody. Thank you for coming. So we have Omri. Every time Omri comes to BSides, we just make him talk because he does really cool stuff. So he's been to 4 here so far. Every time he comes to Vegas, he speaks. He's going to be talking about installing rootkits on Windows 11. So pretty cutting edge, about as modern as it gets for what he's doing. So without further ado, we have Omri. Thank you for coming.
Hi everyone. Thank you for coming. I believe we are wrapping up today. As I was introduced, my name is Omri. I'm currently in charge of the security research in Fortinet's R&D site in Israel. And sorry? No, it's okay? Great. Most of my work is around endpoint security. As I was introduced again, I'm not the first. It's not the first time I speak here, and I have spoken in a few other BSides events in other places as well. What we're going to talk about today is a bit of a background and introduction about driver signing, enforcement, a bit how it's being protected on Windows, and a couple of new techniques that we found in order to bypass those new protections. And hopefully we'll show the live demos and everything will work without a hitch. And then we'll talk about some suggestions that we have in order to prevent that. And we'll give you a quick summary of basically everything we covered. Okay, I'll just start off with a warning. What you're going to see here today is going to be rough, and not because of the content, it's because I do my own slides and I'm really, really bad in Photoshop, so I apologize in advance. Okay, here we go. Basically, what is driver signing enforcement, or in short, DSC? Code integrity basically is a feature that has been introduced over 15 years ago. For drivers, it means that basically you have to sign them in order for you to be able to load them into memory and execute them. Every time you want to do it, they are being checked and validated, and basically it gives you the option to improve the security of the operating system, because then you can know, once they're signed, from where they came from, and there is some assurance that they haven't been modified when they got to you. The way it works is during that basically the Windows kernel, when it starts running, it uses another library called CIDLL. When it starts running and the machine boots, basically it goes from the call flow you see on the left, and eventually it sets some global flag that says it's enabled, and then calls CIDLL with the CI initialize function, giving it a pointer to a callback structure that CI will initialize and set addresses of callbacks to it, and it will set another internal flag, the CI options, that will state that it's also on. Then when you come to load the driver, basically the operating system, before it maps it into memory, will validate the driver, the signature itself on the driver. It will call eventually 2 functions, the validate image header and validate image data. Those are wrappers basically that will eventually call CIDLL. And on the right-hand side, we can see an example of the disassembly of one of those wrappers. All it does is check the flags, check the global flag to see that DSC is actually enabled, and check the callback, the specific callback it wraps is actually valid and not null, and then it will just call it. Simple as that. Now, there have been a few changes. What I've described is pretty much how it looks on Windows 7, which is pretty old by now. Along all few years later, basically from one OS version to another, there have been slight changes. From Windows 8, we no longer have the global variable in the kernel itself, only in CIDLL. The callback structure also changed a bit. They added a few other callbacks, and some of the important callbacks that we mentioned before. The placement in the structure changed, but essentially those callbacks are still there. And one other major thing is that basically now when the signature is validated, then only the image header callback the validated image header callback is being used. So how do you bypass code integrity? So the easiest thing to do, the most straightforward thing to do is use a digital certificate to just sign your payload. Either that you steal it, or if you somehow trick some certificate authority to issue you such a certificate, then you can just do it. The other option is basically use some exploit and gain code execution in kernel, usually some shellcode or warp chain, and then you can just load up your driver if you want to, reflectively, but it introduces some complexities. So the last option that we have is basically just turn off driver signing enforcement on runtime, and then load our driver and continue. How it's actually being done? As I said, it's just flipping some flag. So one of the flags basically is being changed on runtime. You write to it and change its value. Since it's not exported, we need to find it somehow. So basically, there are simple pattern that you can search for, and then you can find those flags. This is how it's being done right now by some APT groups. Then you overwrite the value, and you just load your unsigned driver. And once you're done and your driver or rootkit is loaded, basically you have to quickly restore the flag because you want to avoid some protections like patch guard that we'll cover in a bit. The way that you get the ability to write to the kernel is usually by bringing your own signed driver or bring your own vulnerable driver and just use it in order to load it first, because it is signed and then it will bypass it will just go through the check. Just go through the check and the validation, and then you can just use it to read and write to the kernel however you want. And then you can just flip the bit with it and load the rest of your payload. So in recent years, there have been quite a lot of cases that use DC tampering. We can see some of the statistics here. In the last couple of years, basically, there's a bit of a spike here from an average of one group a year that is being reported on. We got to an average of about 5.5. So it's quite a lot. In light of this critical attack path, Microsoft did try to mitigate it and fight against it. The first protection that was used is patch guard. Again, it's quite an old feature. It prevents from modifying the kernel or its code for long periods of time. Once it detects some change, it basically will cause a blue screen, and what will make the system stop. But with every new release of Windows, basically it's being improved. And from Windows 8, again, it started protecting code integrity and driver signing enforcement. The next protection that Microsoft tried to introduce is the signing policy itself. So first off, you can just sign, can just use any certificate to sign your driver. You have to acquire a certificate from a specific subset of public CAs. So that pretty much prevents you of like installing your own CA on the machine and running your driver. And then from Windows 10, they did a bit of a radical change here, and they force you to provide your driver to them in order for them to place, for them as Microsoft, to sign your driver themselves. So it's not only that you signed it, but they have to sign it as well. And if you are an attacker, you don't really want to hand out your payload to the defender. It's not exactly something that you're aiming for. Usually you try to do the exact opposite of it. And, but still, it didn't really help, because there are already drivers that are signed, and they can be abused, as we said. So for that, basically, Microsoft implemented a block list, just in order to make it harder to gain that that kernel write primitive. It's enforced via Windows Defender application control. But the downside for it is that basically, if you get a new vulnerable driver that you're not aware of, so attackers can just find some new samples like that and use that. So it's really not a proactive measure. The newest mitigation, the newest protection that Microsoft tried to use is called the KDP, or Kernel Data Protection. Basically, it uses the newest and more advanced features for virtualization-based security, also known as VBS, and leverage the fact that now the kernel cannot do whatever he wants inside of kernel space, but he has another virtual machine that he has to cooperate with. It's called the secure kernel. So basically, drivers or every software in the kernel can now request from that secure kernel to basically remove the write permissions from certain locations in memory that he wants to keep as read-only. And the hypervisor will basically enforce those protections. But what's important to note here is it does it only for the permissions, not for the mapping between the virtual address space and the physical address space at the end. How it looks like in Windows 11, so CI/DLL was opted in. Basically, some programmer in Microsoft, some developer went to the code base and added another API call. As you can see here, now CI options is being protected. And the flag itself was moved, the variable itself was moved to its own separate and new section in the PE. And basically, it's along with all the data that needs to be used for the driver signing enforcement. So let's talk about our new techniques now. If we need to recap for a second the tampering procedure, basically we first locate whatever we need to find, whatever internal variable we need to find, and then we overwrite it. Then we go to load our driver and revert the state, and we'll focus on those two initial steps because those are what matter here. The first technique, we called it page swapping. It's very not very creative, but kind of explain what it does. So instead of changing the value of the page, let's just point the page to another page, and this is how we're going to change the value. If we have the CI policy page, if we can see the mapping here and the permissions on the PTEs, basically every write we'll try to do to it won't matter. But instead, we can create a new page that we'll own, and it will have the right permissions. And we can set the value that we want for driver signing enforcement to be disabled. But this still doesn't affect the DLL, doesn't affect CI DLL. We need to change how the virtual address mapping. So all we need to do is change the PFN to point to a different physical page, and the rest will do it. The rest will just work the same. Okay. So how can we actually do it? We just explained it in very high-level terms. We need to be able to access the page tables. Those are found in a space called PTE space in the kernel space, sorry. And basically in that area we can access the PTEs directly using their virtual addresses. It really cuts down on the number of reads and writes we need to do from user space to kernel, because we can just calculate everything pretty much everything in advance. And it really simplifies the implementation of the technique. Now, from Windows 10, the PTEs are basically randomized in the memory due to KSLR. But luckily for us, we already presented some old research here in BSides that we show how with a single kernel read, basically we can find the new PTE base. Basically, there is an exported function in the kernel that holds the address, so we can just find its address of the function and then go to the offset and read from it the new randomized base. So, if we go again about the technique, we need to allocate a new writable page in the kernel. Then we need to find CI options, the flag, just as we did before. This is done exactly as it's being done in the wild. Nothing new in this area. Then we're gonna read the new PTE base, and we're gonna read the PTE for the flags page, and read the PTE for our page. And from there, we need to copy the entire page from the old one, from the DLL to ours. So nothing else will break. Then we need to modify CI options in order to disable it in our new page. And then we just swap the PFNs as we talked about before. Load the driver and restore the original PFN later on. So this is a bit complicated. I wasn't very happy with this. It requires a lot of reads and writes into the kernel, and it pretty much means that this technique is not really feasible. Happily for us, we found some workarounds and adjusted the technique so it will be a bit more realistic. So instead of allocating a page in kernel, we can allocate the page in user space. There's nothing fancy about it. We're already running code in user space. And then we'll do all the locating just as before. Nothing special here as well. We need the free kernel reads. We initialize, instead of copying the page, we can just initialize it with the default values. Because this page is now, all the variables in this page are now being placed in a separate section, especially for KDP, because of KDP. It's quite easy to predict what those values are going to be, so we could just set them in advance. Then we disabled, once we initialized it, we disabled the flag. And we switched the PFNs, we loaded the driver, and restore the original PFN. So let's go and start our first demo. Let's see. Sorry. Okay. So first off, we'll see that we have a Windows 11 here. Okay, it's a pretty recent build. I think it's from 2 or 3 weeks ago. The insider preview build. We can see that we have VBS running, but only credential guard is on. KDP doesn't appear here, but in a second we're going to show you it's working. So the first stuff, basically, we'll go, in order to show you, to prove that KDP is actually working, we're going to show the existing implementation of DSC tampering in the wild, and it will result in a blue screen, hopefully. Yay. So if you can see, it should say that there is an attempt to write to a non-writable location. And the screen is a bit far from me, so I don't really see it. Revert to the snapshots. And now we're going to hope for a different result that won't be a blue screen. So first, we're going to install our driver, our rootkit, and we're going to try to run it. And we see we get an error that the driver is not signed. Just so you see, I'm not messing with you. Properties, right? And there is no signature over here. Now we're going to run page swapping, and it's waiting for us to load the driver, which we did. And you can see our rootkit is doing some debug prints just to show us it's alive. If we're going to stop the rootkit now, we see it's stopped. And if I try to run it again, I get the error again. Thank you. So to sum everything up, on the left, we have what's called flag flipping. This is what we named the technique in the wild. And we compared it to all of the variants for page swapping. And we got to a variant that it's quite decent. It requires only 3 kernel reads, or a bit more if we don't want to completely rely on the default values, and a single kernel write. But we still weren't exactly happy, because if we can see on the column on the left, the current technique in the wild doesn't do any reads, doesn't do any kernel reads. So we continued to look at how we can improve upon it. And the next technique that we found is called Callback Swapping. Again, very creative name. Basically, what we'll try to look at right now is find another point of data that is not protected, even before that CIDLL is used. Basically, when the callback the callback in CIDLL is being executed, at the end the expected result should be 0. The callback should return 0. So what about if instead of going all the way through it and hoping that it will return us 0, what if we can just use another callback that returns the 0 directly for us immediately without any validation whatsoever? Happily for us, the callback structure in NTOS kernel is not protected by KDP. So it means that we can freely write to those locations. But we still need to find a way to locate it, because, again, it's an internal variable. So how can we do it? So basically, if we look at the initialization phase, the CI initialize function is imported, and then we can look for a call that is actually referencing that importable entry. And once we do find it, we can just go back and look for the parameter assignment in the registers. Once we do find some such assignment, we're just gonna check that the address that it points to will lead to the data section, and the data there will be uninitialized. And that's how we know we found the callback structure. Next up, we need to find a new callback. Basically, there is a very easy way to do it. If we use exported functions from the kernel itself, we can just use getProc_address and get those functions, get the address of those functions. And if we want to be a bit more creative, we can look for exported functions in CIDL itself, or some gadgets that will result in the same return value. For instance, as we can see here in CIDLL, the benefit for that is that the writes that we need to do to the kernel will be smaller, because the addresses are not as far apart once we look in the DLL itself. The hardest part here is finding the original callbacks. Basically, we want to do it without reading the kernel, without looking in the kernel, in the callback structure in the kernel, and all of those functions are internal and not exported in any way. So what we can do is look for in the DLL's initialization function for the assignment of the fields of the structure. Okay, this pattern repeats itself pretty much in every version of the operating system. And then, in order to verify that we actually found the right addresses, or that the addresses that we got are actually for functions and not just some random area, we can check the exception directory for entries that will have the same start address as the offset that we found. So with that, we completed our locate phase, and the overwrite is pretty easy. We just write the callback and load the driver and restore the original callbacks again. Let's try another demo. Okay, so I'll skip the reverting the machine because we already see that the driver isn't loading. And it's already installed. Okay. Great. So as you can see, we first disabled DSC, loaded our driver, and then we restored it. For a second, for one last try, we're gonna just make sure the restoration worked. Just see. Now we stop the rootkit. Yeah. And we can't load it again. Thank you. So if we compare our techniques, we managed to find some technique that will actually looks pretty similar to the one that is used in the wild. We can do everything that we need with single kernel write. In the demos that I showed you, I used the known vulnerable drivers that are being used by attackers in the wild, so it's completely feasible. And from here, we try to figure out some way that we can improve the situation and not just like show you new techniques that you need to worry about. What we thought about was basically, why not just confirm the state of DSC when we know a driver is being loaded? And once we do, we can decide how to act. We can find those internal variables ourselves, same as attackers do. They're proving it to be stable so far, so why not do it also ourselves? So basically, when we boot, or when our protection starts, we can kind of assume that the system is not currently compromised because of all the other protection mechanisms that prevent the compromise to be for a very long period of time. So when we start, we kind of assume we're in a valid state, and we can just capture it, meaning that we're going to copy the callback structure and the values of the flags to a different location. And then we need to figure out how a driver is loaded, or when a driver is loaded. And not just that, we need to be able to manipulate that moment in time. We need to be able to control it. So this can be, the driver loading can be intercepted by placing a hook in user space on the API call, but that's not really robust. And in kernel, we can leverage some callbacks like the registry operation callbacks or file system callbacks using a mini filter driver. For registry callbacks, we can check once we see access to registry keys of drivers, and then we know, and if they are happening when the current process is the kernel itself, we'll know that it's most likely originates due to a driver loading attempt, or when the driver is being loaded to memory, when the driver file is being loaded to memory via a section, or it's being mapped into memory. It's even before it's being loaded. Then on those points, we can just compare, we can just find the variables again and compare them for any change. And if there was a change, prevention is pretty easy. We can just block the IO request in the callbacks, or we can restore the values of the variables and let the system do its own work for us. So just to summarize here, I think that DSC tampering is still feasible, at least with callback swapping. Data-oriented mitigations like KDP, they are pretty tricky to implement, and also some of the people in Microsoft also think so. So I'm not really sure what was the goal behind it. Defenders can use the mitigation that we suggested. We're going to release, hopefully, the source code for it, so it will help speed up the process. And the final thing, and I think it's the most important point of this talk, is there is a real solution for it. Microsoft did a pretty good job on developing virtualization-based security mechanisms, one such as HVCI. It exists for 7 years now, but it's still not as common out in the field. Hopefully it will be more adopted in the next few years. Basically, what it does, it's leveraging the fact that we have a secured space that is actually being separate from the kernel, that the kernel can't really access, and there it performs an additional validation once we load the driver. It has its own set of policy and its own copy of the CI policy, and it validates it as well. And in order for you to get execution permissions in the kernel, you have to go through it. Only it can actually set the execution permissions, because you have 2 sets of PTEs, as we said, that you need to be able to set the permissions on it. Same as for write, you also have the execute permission on that PTE. And basically, in the end, that's the real solution here. So if you can, just make sure you turn it on. That's it. Any questions? Thank you.